If you look closely at the number and numeration section of the JAMB Mathematics Syllabus, you'll spot a specific requirement right here: conversion from one base to another, including fractional parts. Converting standard whole numbers between bases is a routine skill, but examiners know that when a decimal point flashes in a base conversion problem, the failure rate spikes. It's designed to catch you off guard. In the next 6 minutes, we are going to walk through a systematic, step-by-step method to convert any number, especially those with decimals, in both directions. Mastering this specific rule secures marks on exam questions where most students just guess. Let's look at this animated diagram. A number base is simply the number of unique digits a system uses to count. Our everyday system is base 10, using the digits 0 through 9. Base 2 only uses 0 and 1, while base 8 loops from 0 to 7. On this whiteboard, we have a real past paper question. Change 71 in base 10 to base 8. To convert a base 10 whole number into a new base, we use a process called repeated division. We start by taking 71 and dividing it by our target base, 8. 8 goes into 71 8 times, leaving a remainder of 7 on the right. We divide that answer, 8, by our target base again. It goes in 1 time, remainder 0. Finally, we divide that 1 by 8. Since 8 cannot go into 1, the result drops to 0, and we carry that 1 over as our final remainder. The process stops when the whole number reaches 0. Here is the strict rule for whole number conversions. You must compile your remainders reading from the bottom up. That gives us 107, or 107 in base 8. When you divide downwards, you read your remainders from the bottom up. That covers whole numbers. But what happens if the exam question asks you to convert 71.25 instead of just 71? On the right side of the board, we separate the decimal fraction, 0.25. For decimals, the operation flips. Instead of repeated division, we use repeated multiplication by the target base, which is 8. Multiplying 0.25 by 8 gives us exactly 2.0. For the decimal side, you isolate the whole number results from your multiplication. Unlike the division method, you read these results strictly from top to bottom. Because our decimal reached 0 immediately, our answer is simply 0.2 in base 8. We merge the two sides back together. 71 gave us 107, and 0.25 gave us 0.2, resulting in a complete answer of 107.2 in base 8. Whole numbers divide down and read up. Fractions multiply down and read down. Now we need to reverse the flow and translate a foreign number base back into our standard base 10. We do this using the expansion method. Here is the number 11.01 in base 2, written out with a vertical divider separating the whole numbers from the fraction. To expand this, we assign a positional power to each digit. We map positive integers moving left of the decimal and negative integers moving right. Pay close attention. The first position to the left of the decimal always starts at power 0. Next, we multiply every digit by our original base, 2, raised to its assigned power. We then simplify. 2 to the power of 1 is 2. 2 to the power of 0 is 1. The 0 term cancels out. For negative powers, they represent fractions. 2 to the power of negative 2 becomes 1 over 2 squared, which is 0.25. Adding these together, 2 plus 1 plus 0 plus 0.25 gives our final answer of 3.25 in base 10. The value of each digit is determined by its distance from the decimal point, defining which base power to apply. Let's review the two frameworks on this cheat sheet. Going from base 10 to a new base, divide and read up for whole numbers, multiply and read down for fractions. Going from a new base back to base 10, expand the number using positional powers, making sure your whole numbers start at 0 and your fractions use negative powers. Try applying these rules right now. Convert 10.5 to base 2 and drop your answer below. You now have a reliable system to handle fractional base conversions, securing your marks on one of the trickiest segments of the syllabus.